We're going to be covering section 0.2, new functions from old. And we want to remember from Algebra 2 that these are functions that we combine, so these are combinations. So we're going to take two functions and combine them. And we want to make sure that we note that the domain is going to be the intersection of those two domains, okay? And when we talk about fractions, we have some other issues, okay? Notation on the right and the left, your other right, is going to be familiar to you, so you want to make sure you can read both. All right, example 1, you're given one function that is a square root, and you're given a second function that is linear. And so what you want to do is you want to look at both of those and read the question, noting that there's two pieces to each question, a domain and a formula. So if I look at the domain of f of x, I should note the important part here is the square root. And so looking at that, I need to note that the domain is going to be x has to be greater than or equal to 2. Whereas for g of x, the domain is all reals. And again, noting yesterday's lesson, notation is completely up to you. So now when we take f plus g, you want to look at that, and where do those two overlap between here and here? The only overlap in the domain is going to be x greater than or equal to 2. Okay? For f minus g, same thing. For f times g, sure, the domain is going to be, again, and for f divided by g, we have an additional issue, and that is going to be the fraction in the bottom. So we want x greater than 2 such that x cannot be 3. And you'll see why once we do the formulas. So f plus g is going to give us 1 plus the square root of x minus 2 plus the function x minus 3. And you can combine like terms or leave it at this point. F minus g is going to give us 1 plus x minus 2 square root minus, notice the parentheses because the minus would apply to everything after. F times g is going to be multiplied out, FOIL, distributive property. And here's the one that I said we need to mention, and this is f over g. And that's because fractions have an inherent issue, and we should all remember that in math, this bottom can never be equal to 0, which means x cannot be 3. And then we have the same issue here, x has to be greater than or equal to 2. So all there is x greater than or equal to 2, such that x cannot be equal to 3. All right, so there's the example. Read through it. It wants to show you why the domain of fg is not the same as the domain of h of x. So h of x is x, and we know that the domain to that is all reals. That's just a line. But fg is equal to the square root of x times the square root of x, which if we simplify, we would get x. But the important thing to remember here is this would have to be a positive, and this would have to be a positive, which means this has to be positive, so we would have to have either an absolute value there to make that function, or we could say, without the absolute values, we could just say it's equal to x, but all reals greater than or equal to 0, or x is greater than or equal to 0. Okay? That has to be positive. Okay, so the definition now, we're going to move from combinations into composition, where we're actually generating a third function, okay? And all we're asked to do here is to find f of g of x and g of f of x, okay? So remember, that means for f of g of x, we're going to plug g of x into f of x. So anywhere we see an x, we're going to plug in the square root of x. So this is really going to be the square root of x quantity squared plus 3. Again, very important to note the domains of the individual functions. This has a domain of all reals. This has a domain, x must be greater than or equal to 0. Okay? Now, if I leave it like this, I can see it pretty clearly. This has to be greater than or equal to 0. If I simplify it, it looks like that, and I want to say all reals, when in fact it isn't. Remember, this number would be the square root of x times square root of x, which would be a positive times a positive, so this number would have to be positive always, okay? So, domain and range is going to depend on your original functions. Whereas h of x, g of f of x here is going to be plugging f into g, so that would be the square root of x squared plus 3. Okay? Now, the problem doesn't actually ask us for the domain, it just says to find f of g of x and g of f of x. But important to note in this case that this function, as it stands, the domain is all reals, because there is no restriction there. Okay? This would have to be positive, and you can see would be positive everywhere. So, no issues. All right, example 4, f of g of h of x, which means that we're going to take h of x, plug it into g of x, and then plug that into f of x. So, inside out. Written, it would look like this. So, remember, we want to work inside out. So, h of x plugged into g of x gives me 1 over x cubed, so I want the f of 1 over x cubed, which would give me the square root of 1 over x cubed, which would give me all of these. And any of those notations is acceptable. All right, example 5, express sign of the quantity x cubed as a composition of two functions. First things first, when I look at that, and then you look at that, what you want to see is you want to see it as two functions. That is the sign of something, and it is the something else cubed. So why not look at this as f of x is equal to sine x, and g of x is equal to x cubed. We can call it x, but in this case I just use parentheses. But that would give me f of g of x. Okay, in example 6, a couple of things. Everything that you need is on the board, but I want to make sure that you understand. The graph given for the square root of x is present. The graph given for 1 over x, present. And the actual answer, as noted in the book, is here for the question. That's actually the combination of those two. The important thing to note here is what you're really doing is adding y values. Who cares what the actual value is? Let's just make relative numbers. Let's say that this is a 1 and this is a 2. These are both positive values, and that would give us our 3 here. So we're actually adding up this value and this value to generate the third value. So with the combination, we're adding the y values. Okay, table on translation principles. Review, Algebra 1, Algebra 2, pre-calc. The important thing to note, these two are vertical shifts. Vertical shifts are done at the end. Notice that these numbers are attached. Now, you could have a function written as 4 plus f of x, and that would work just as well. The other two are actually horizontal shifts, and important to note that the horizontal shift is the right-left, and notice the inside. It's actually the opposite, so counterintuitive. So this says minus 2. It actually really means right 2, not left 2. Whereas here, minus 2 actually means down. So inside is opposite. Okay, so we want to sketch the graph. Go ahead and pause here and attempt to sketch either of those. Okay, when I sketch these, I like to use a shortcut, and so I want to look at my parent function, which is the square root of x, which I know looks like this, and so something like that. And so if I point out with another color these points, those are going to become the important points when it comes time to translate. So these are both inside connected to the x. That's important. So let's do the first one first. That's minus 3. Well, inside is opposite, so minus 3, no, it really means right 3. So 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So the x value doesn't change so much as when I move my dots, I'm switching them this way. So it's actually the y value stays the same, and all I want to do is change the x. Okay, moving on. The second one, let's do that one in black, and the plus 3 really means left 3. So we want to go 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3, and then connect the dots. Okay, so you could use a shortcut, or you could actually generate a t-chart. Example 8, sketch the graph of y equals x squared minus 4x plus 5. This is a review of Algebra 1, so please pause now and sketch the graph. Okay, so what we have here is a parabola. I know that because of the x squared. It does not factor, so I'm going to go ahead and use my quadratic formula info and recognize that that's where my vertex would be. First things first, I want to note that the y-intercept is at 5. 1, 2, 3, 4, 5. Put that in. Now I want to find negative b over 2a, so I'm going to go ahead and do that. And when I do that, I'm going to get 4 over 2, which is 2. And now I want to plug in 2. So 2 squared. And 4 plus 5 is 9, 1. So my vertex is at 2, 1. I want to use my algebra cheat to go over 2 at 5 and complete my parabola. Reflections tend to be a little bit harder. Reflections happen either over the x or the y-axis for us. The first one shown here is a reflection over the y-axis. Important to note, we're actually changing the sign of the x value. The y value output is exactly the same. When it comes to reflecting about the x-axis, it's the y value that changes. So the minus sign is on the outside and thus changing the y value. Sketch the graph of y equals the cube root of 2 minus x. Go ahead and pause now, and then sketch that video. All right, so it's a cubic function, and I'm going to go ahead and I'm going to rewrite it because I want it to be in a form that I can see. And that's a cubic function. And I'm going to go one step further because then I can see two things happening. I can see a reflection, and I can see a shift. So when I do this, the first thing I want to do is start with the reflection, because this negative sign right here tells me that I'm going to reflect it over the x-axis, and this minus 2 tells me I'm going to move it right 2. So what I want to do, if I can't do the shortcut, I want to use a t-chart and just start plugging in some numbers and see what happens. If I were to plug in 2, negative 2 plus 2 is 0. If I plug in 1, it's 1. If I plugged in, I don't know, negative 7, it's 30. No, it's not. Okay, let's go with those. Let's skip that. I'm doing that in my head. Bad idea. Okay, so let's go with this one. So my cubic function normally looks like this, something like that. And what I want to tackle first is the reflection. The reflection is going to go like this. Is going to switch it. What was negative x values are going to become positive x values, and what was positive will become negative. And then I want to shift it minus 2. So minus 2 actually means right 2. So I'm going to take that and go 1, 2, put it here, 1, 2, put it here, 1, 2, put it here, and then something like that. Okay? And if that's all true, then I should note that when x is 0, which is what I have, I get some positive value. Makes sense. Okay, so final graph looks like this. Again, noting first the reflection and then the shift to the right. Okay, example 10. Sketch the graph of y equals 4 minus the absolute value of x minus 2. So I'm going to go ahead and do it this way. And I want to notice, hopefully you'll notice 3 things. 2 and 3. The first one means a reflect. The second is a horizontal shift. And the third one is a vertical shift. And this means up 4, this means right 2, and this means to flip it over the y-axis. So, I know a couple of things. I know that the absolute value function looks like a V for victory. And so this would look like a negative absolute value function for my parent function. So what I want to do is I want to take it and make a sketch of a negative absolute value. But now I'm going to take that negative absolute value and I'm going to move the vertex over 4 up 2. So this dot is going to go 1, 2, 1, 2, 3, 4. And that means every point thereover is also going to be shifted 1, 2, over 2, and up 4. Okay, stretching and compressing. I call it shrinking and stretching. Bigger numbers make it taller. Littler numbers make it shorter. Again, these are y direction. Okay, these are in the vertical. Okay, here we can make them longer or shorter. Okay, so bigger number actually makes more of them happen. So this is actually a shorter wavelength, but it's the opposite. When it's inside, it's the opposite. Instead of having 2 humps, we have twice as many in the same amount of time. So that's what you're really looking at. And same thing here. Instead of having the full 2 humps, we actually have half. Okay? We're actually stretching it out. We want to make it longer. So less occurs within that space. All right, so these are x direction. I use the word wavelength. It's just the number of waves happening here. Don't worry about that. Okay, so symmetry. You can have symmetry about the x-axis, the y-axis, or the origin. Symmetry about the origin tends to be like your odd-even functions. That's what you would think of. And then, so you're specifically looking here at what would be your odd functions, opposite quadrants being equal. Y-axis, you're looking for the y values to be the same, and x-axis, you're looking for that your y values are exactly opposite. Okay, so here we're looking for exactly the opposite. Okay, here, notice exactly the opposite. Okay. Using the theorem, find the symmetries of the graph x equals y squared. So, because this function is defined in terms of x, we need to define in terms of y. And I said function, but it's not. It fails the vertical line test. So it's really just a graph. But f of y is equal to y squared. So what if I plugged in f of negative y? Do I get the same output? If that's true, then I am symmetrical about the x-axis, meaning my y outputs are going to be exactly the same, even though when it came to the input, I changed the input by a sign. A function f is said to be an even function if you can switch the input by sign here, and you get the same output. It's an odd function if when you change the input, you also change the output. which becomes extremely important in terms of language, inputs and outputs. What you're going to do now is you're going to tackle the quick check exercises, and those are on page 24. And once those are completed, you will be ready for the discussion in class.